Okay, in this lesson, we're going to talk about a different type of angle, inscribed angles. For comparison and contrasting, we're just going to remember what a central angle is. So the central angle is an angle whose vertex lies on the center of the circle. So remember, when I draw an angle, the vertex is the point where the two rays are connected, the two endpoints of the rays. That vertex on an angle, if it lies also on the center of the circle, that is called a central angle. Another reminder is the central angle intercepts an arc. It's the arc that's inside the mouth of the angle. Sometimes I extend the sides of the angle past the circle so I can clearly see where the intercepted arc is. It's the part of the circle that is in between the two rays that's on the interior of the angle. I say it's sort of like Pac-Man. If that's the mouth, it's the part of the circle that it's eating, that's like closing and opening. All right. Now, a reminder about the arc intercepted by a central angle. The reminder is that its measure in degrees is the same measure as the angle itself. They've both opened up the same amount of rotation around the center point. Okay. The next angle we're going to look at today, we're going to study what it means to be an inscribed angle. So first of all, to remember the language inscribed, I could say something like, this is a triangle inscribed in a circle. What that means is the corners or the vertices of the triangle are on the circle. So again, the triangle is inscribed in the circle. The vertices are on the circle. So I use that. I understand what that means. I think you might have heard that before. So I use that to try to remember what an inscribed angle is. So here's my angle. Its vertex is not on the center. Its vertex is now on the circle. So anytime the vertex of an angle is on the circle, we're going to call that an inscribed angle, okay? And for time, I'm going to just keep going. You should pause, draw the picture, write down the definition, okay? So the inscribed angle is an angle whose vertex is on the circle. And if I look at the arc it intercepts, they're no longer equal. That's for central angles. The measure of this arc is going to be 110 degrees if the angle is 55 degrees. How do I know that? We're going to take a look at how we could figure that out. But that's going to be a fact that you want to remember, that the arc is 2 times the inscribed angle, or double. The arc is double the inscribed angle, and vice versa. If you knew the arc, the angle would be half of that arc, right? So this one, you knew the angle, you double it to get the arc. Vice versa would be true the other way. Here's a little activity that can kind of show you how we can prove this. So if I consider this inscribed angle here, right? It's an angle, to review the vocab, whose vertex is on the circle. Therefore, it's an inscribed angle. I want to compare the measure of x with the measure of the arc it intercepts, y. I want to compare that red angle measure with the purple arc measure. So we're going to get those two measures in two different ways. I know the purple arc measure is going to be 76 degrees because if I look at this dotted line, I've got a central angle here with a measure of 76, and we know that the central angle and the arc are the same. Now, how can we find that red angle and prove that it's half of 76? Well, if that's 76, I know that I've got a linear pair here. So 180 minus 76 would be what, 104? So this angle right in here is 104 degrees. And these questions are all leading us through that. So the measure of arc AC is 76 degrees. The measure of angle BOC, because it's a linear pair, I'll use a different color than red because it's not the red angle, of BOC is 104 degrees. And now we notice that these guys here, I guess I'll do it in red, are both radii, so they're congruent in length, which makes that an isosceles triangle. So that means I could do 104, the triangle sum with it. So 180 minus 104 is 76. I divide 76 by 2, and each one of these angles will be 38 degrees, because that's half of 76, right? So I just have shown that this angle here, the inscribed angle, is 38 degrees, and the measure of the arc that it intercepts is 76 degrees. So the measure of an angle inscribed in a circle is going to be is equal to half of the arc. Whoops, there's no E on arc. It intercepts. Okay, so in this case, if I had 92, half of that would be what, 46 degrees? Because here's my inscribed angle. And the arc that's in the mouth of that angle is right here, and that's 92. And we just learned that the angle, the inscribed angle, is half of that arc. Now, I also know that the central angle intercepts the same arc, so that central angle is 92, but the inscribed angle is 46. All right, so here's an example we could do to practice this. If I know the inscribed angle is 52, I could double it to see the arc it intercepts. So I like to extend the angle out. So it's clear to me that this is the arc that 52 intercepts. Since the vertex is on the circle, it's inscribed. So that arc measure is not 52. It's not the same. It's double. It's 104 degrees. Now I notice that this central angle intercepts the same arc. But now that it's a central angle, then its measure is going to be exactly 104 degrees. Here's a little bit trickier one. We're going to look at this as two half circles. So for the first part, we're going to ignore the bottom half of the circle. I'm just doing a bunch of examples so you can see how this works. So if I ignore the bottom half of the circle, I can do, this is a semicircle. And so this arc over here, AP, has to be 180 minus 156. So that's going to be 24 degrees. And then this angle, Y, intercepts this 24 degree arc. And since it's inscribed because its vertex is over here on the circle, I'm going to cut it in half and get 12 degrees. The angle is always half of the arc. The bottom half of this circle, we're going to do it the reverse order. So now I'm going to ignore the top part. So on the bottom half, if the arc is 35, this is an inscribed angle because its vertex is here on the circle. So I double it to get the arc it intercepts. So if I double 35, I get 70 degrees. I know that this is a semicircle on the bottom half, so it has to equal 180. So if this part is 70, then this part is 110 degrees. Let's move on to another conjecture. I'm going to go into the notepad here for this one. Inscribed angles that intercept the same arc. So here's an arc we're looking at. Let me get the pen tool going here. We're looking at this arc, and I'm going to pull in two inscribed angles that intercept that arc. So I know that that black angle is half of that arc. That arc looks to be, say, 90 degrees. Whoops. That looks like it's 1/4 of the circle because that central angle is 90 degrees. So it looks to be 90 degrees. So that black angle is going to be half of that, 45. What if I pull in another inscribed angle? I can make many inscribed angles that intercept that same arc. This blue angle also intercepts that same arc, and it's inscribed again. Remember, they're both inscribed because, let's see, I want to go blue on this guy. Inscribed means that the vertex is on the circle. That makes it inscribed. That's an inscribed angle, and it intercepts that same 90-degree arc, so its measure has to be half. So this conjecture is going to say inscribed angles that intercept the same arc are congruent. Or you could say equal in measure, right? They're both 45. I could draw another one over here. That'll be 45. I could draw another one here. As long as it goes to the same endpoints on the arc, they're all 45 degrees. Again, you need to be pausing and writing stuff down. Sorry, I'm not feeling well. I've got a cold or something. So here's a practice example of that conjecture. This video is getting to be a little long, so we're going to skip that. Angles inscribed in a semicircle. So here's a special case when your inscribed angle intercepts half the arc, like half the circle. So look, if I extend, here's an inscribed angle. It's inscribed because of that vertex. It intercepts half of the circle. Well, what do we know half the circle to be? 180 degrees. So the inscribed arc is the inscribed angle is always half of the arc it intercepts. So that inscribed angle has to be 90. And based on the last conjecture, there's many that I could draw. I could draw another inscribed angle that intercepts that same half a circle. It's inscribed because of the vertex. That's going to be 90 degrees. So any angles inscribed in a semicircle. So like here's my semicircle. You kind of inscribe it where the ends are on the diameter and the vertex is on the circle. Whenever that happens, angles inscribed in a semicircle are all right angles, or I'll just say are 90 degrees. The parallel lines arc intercepted conjecture. If I have some parallel lines, whoops, I got to go to the notebook for this one so I can pull it. Okay, so if I have some parallel lines, I'll put one there and one there. The arcs that the parallel lines intercept, that means the arcs that are in between those parallel lines, there's two of them, they're always going to be the same. If that one's 12 degrees in measure, that one's 12 degrees in measure. If I kind of change that line, I want to make this one so it looks parallel, maybe like right there. And I put, let's see, I can space them out. I can put them close together. You can see that those arcs in here will be the same measure. Or even if I space them out, you could see that, let me get rid of this stuff. If I space them out, you can see that these arcs are the same measure as long as the lines are parallel. Okay? So it's always the arcs in between the parallel lines that are the same, not these guys. These guys out here don't have to be equal, right? One way I could show that is if I put these lines close together. It's clear that these red arcs are not the same. This one and this one are not the same. But these guys are the same. This one in here and this one in here. So parallel lines intercept congruent arcs on a circle. There's your notes. We'll do some practice with this in class.